Again, I would like to thank AICTE and also Modern College of Engineering, which is basically part of the Progressive Education Society. Really, they have done fantastic job. You have done a fantastic job of organizing this FDP. So let's move ahead with today's topic. So one of the motivation actually during first part of my talk, I will talk about wireless charging. Here you can see in this picture some of the modes of transportation that may become autonomous, driverless, or without any pilot. So for example, buses, right? On top left hand corner you can see I talked about some e-bus applications yesterday, and this is a bus, as you can see, electric bus in our automotive center of excellence being tested for characterization of the battery pack on the dynamometer. You can see this bus is completely driverless. So we have tested our autonomous bus, e-bus, electric bus on campus in our university. Secondly, we are also doing some projects on drones. I talked about it, and I said today I will talk a little bit more about drone applications. So like somebody asked question about farming, right? So that was a very interesting question. Farming is just one application. We are looking for medical supplies also, like e-ambulance. So deploying the medical supplies to people who are in remote location fast, where ambulance on the road cannot reach in time. So that may be a very nice application for an electric drone, but the drone has limitations of range, battery range. So that issue has to be solved by wireless charging. So buses, drones, electric bike or scooters. See, you can see here there is a electric bike company that we are working with. Wireless charging is happening of the bike. You can see here. We are demonstrating a 1 kilowatt charger here. Then we are also looking at e-ships. So instead of having so many batteries on board and making the ship heavy, yes, there are ships which are becoming more and more electric, no doubt about it. But using wireless charging, we can reduce the number of batteries that we carry on board so that it becomes easy for us. So these all four applications and several more we are looking at in terms of wireless charging. Okay, so that is one of the motivations. So autonomous means completely not just driverless, but also completely devoid of, like, independent, you can say, independent of your self reliable is another meaning of autonomous. So we are trying to make all these transportation modes of mobility self reliable, you can say. Wireless charging is an enabler for that. So wireless charging, fast charging can happen through inductive power transfer. Basically, those who know, who are in the field of this research, know that transformer based technology, but through air, can be used for inductive power transfer, energy transfer. So first application, we'll talk about this drone project that we were doing. See it, I came across this paper actually. You can see this slide for a moment. Just look at it and tell me what is the issue. Can anybody tell me what is going on here? See, there is a family of drones network. It's a network, DroneNet. They are calling it a network of drones called DroneNet. It is a paper from Japan. You can see Japanese. Actually, the paper also is in Japanese. I have referenced the paper at the bottom here. I didn't understand anything in the paper. No doubt. I don't read Japanese. I don't understand. But I have appreciated their effort. What they did is basically connecting the drones through cables. And there is a base station. You can see quite clearly in this picture. Is it clear in my slide? This picture on the left. You can see a cable coming down to the generating station. There is a powering unit which is powering one drone. and then it is powering the other drones. And together they form a network like this. And this network is going to drop this baggage. Okay, that is the job of these drones. Unfortunately, they are limited by the length of the cables. This is the issue. And this was in 2017. You see, January 2017 paper. Not very long ago, like 3 years back. Exactly 3 years back. Today we are in December 2020. Correct? So, unfortunately, the technology, of course, that they used was fine. It did the job. But they couldn't increase the range of this. Like if it has to go to remote location, these cables, how much you will pull, how long they will be, correct? And they have to be powered from the base station at the base. So that is the limitation of these cables. So we thought of going for a nicer solution, more smart solution, and more IoT based solution in wireless charging. So WPT, or wireless power transfer, is something that is catching on last 3-4 years for drones. I'm not talking about the technology itself, and I will come back to that. Just the application for drones and increasing their range. So the network of drones can be such that the drone to drone can be charging each other in the air. Like think of it like refueling in the air, like aeroplanes. Sometimes jets are having fuel infrastructure where the smaller aircraft with fuel can come and fuel with a pipe inside the air, like while flying. Same technology, same philosophy can be applied to drones, where the wireless charger, drone can come and sit on top of the drone that needs the energy, and wirelessly you can transfer the power. Then the drone goes and this drone continues the mission. This is a very interesting work actually. And in fact, to be honest with you, we have started this work with some companies who are drone manufacturers, but also with our Canadian defense military, military application, where they want to see the drone having long lasting life. Ideally, they would like it to be never ending life. Like batteries are a big limitation. Suppose they are going on some critical missions, then batteries can be a big limitation. So that's where we are using these drones. In fact, we are demonstrating these applications. It could be static also. This was dynamic charging, as I said, in midair. You can have static charging. You see on the right hand side, here there is a base station, like, in farming application or any other medical application, let's say. Recently, we are working with ports, marina, like port, seaport. There is in Toronto, we have several ports because we have large lake, and there's a lot of transfer happening through the lakes to the US, trade happening. So ships are coming, etc., etc. We are having drones that do surveillance of these ports, and there are lots of kilometers, miles and kilometers of range that is required. So the Ports Authority of Toronto and different other cities have come and approached us within the Toronto area, saying our drones, we are trying to use drones, but the range is very low. Same story. And I proposed the same application to them, and they were very happy, and we are going to embark on a project with port authorities. So same thing, every let's say 10 to 15 kilometers, we can give range, and this wireless charging pad can be placed strategically, where the drone can come hover over the pad, let's say at 120 mm, or even we have demonstrated up to 30 centimeters range. So they can come, charge and go. Within 2 minutes, you can charge the battery pack of the drone. It's fast charging. So you can size the wireless charger accordingly. Same thing here, it is shown in a demonstration on the top of the roof of a building, for example. So this is the kind of project we are doing with the military. Same application, drone to drone charging using inductive power transfer. This is for Department of National Defense, DND we call it, and Government of Canada is supporting. So you can quite clearly see here some drone application. As I said, up to 30 centimeters we have demonstrated wirelessly charging. You can see quite clearly behind the CRO, you can see the scope. You see here the current waveform. As the drone is hovering over the wireless charger, you can see the charging current, right, being passed from primary coil to secondary. Secondary is the pickup coil on the drone. So as I said, the technology is not new. You can see here that of course there are other products like forklift. Now buses are being used for wireless charging. These are some companies that are leading in the world in this area. Even Siemens has wireless charging. Qualcomm, Bombardier, very famous Canadian company who make trains, Bombardier Transportation, Whitericity, and in fact we work with Whitericity quite a lot. Conductex, Evatran, these are all companies who are in the business of wireless charging. Even now, I believe Hyundai Kona, which I talked about yesterday, electric vehicle which has been released in India, is having wireless charging like this for phones, inside the car. And other Hyundai models also are having. Inside the vehicle itself, a charging pad is given like this. Like you can keep your phone on it and it will charge. So there are nice applications now for this. Imagine also future offices, buildings. Like future can be completely wireless charging, wireless power, no cables, where you can, no need for this network of, it is a mess, when you come to charge your laptop, you charge your phone, everything needs power in the plug. But imagine if it is behind the wall and your whole house is powered wirelessly. Like you enter your house or enter your office and your laptop automatically start charging through the wireless waves, right? Wireless power. So that may be a very nice application for future smart city also. Now they are talking about smart city. Again, same thing, where you have distribution poles. You can see in our cities, like I'm in Bangalore, same thing in maybe Mumbai, Pune, wherever you are, the distribution poles are very hazardous. Like sometimes during rain, poles are falling down, maintenance is required, etc. etc. Imagine if everything was wireless, you don't need all these things actually. Okay, so think about the future next decade. I can see that there will definitely be smart city, no, at least smart, how you say, buildings, offices, homes using wireless power transfer. Okay, and everything was the invention of this gentleman, Nikola Tesla, who you know very well, and I know very well through theory only. We have never met the person, but we have read all about him and his discoveries. He's the father of AC power, as we say. In fact, he demonstrated wireless power transfer initially in the 1900s. His work was unpublished, and also the patent was there in 1900 exactly. So we are talking 120 years back. Wireless power transfer. He basically transferred power from East Coast. In theory, he showed from East Coast of United States, from Connecticut till Midwest in Illinois. He proved that he can transfer the power so many hundreds of kilometers. In fact, thousands of kilometers. Sorry, East Coast till Midwest of Chicago, like near Illinois. So, I mean, he proved half the country he can transfer the power wirelessly without transmission lines. So people thought he was crazy at that time, no doubt. It is 1900 year I am talking about. So today is 2020. We are talking 120 years back. So today again, now everything is going for wireless. As you can see, there is a lot of funding in research, etc. So really, applications are quite abundant. So how does this transfer take place? So simple circuit is shown here. As I said, this you may have studied in second year of your electrical engineering course, like in circuits course, right? So if you pick up Thareja book, for example, circuits, and look at it, mutual inductance definition will be given in AC resonant circuit. Mutual inductance, so M, right? Coupling factor, mutual inductance, very easy theory, which is equal to the or proportional to the value of the inductance of the coils, L1 and L2, as you can see, square root L1, L2. Okay, there is of course a coupling factor K, which has to be multiplied as a product. So K times square root L1, L2 will give you the mutual inductance. See, it is important to appreciate that it is a air in between. There is air in between, there is no core. This is a transformer circuit at the end of the day. Simple transformer, okay? What is happening? Primary winding is there, secondary winding is there. Mutual coupling or mutual flux is there. As you can see, mutual flux is being coupled from primary to secondary. This mutual flux is the key. The mutual flux is transferring the energy from primary to secondary. The whole theory of wireless power transfer is around mutual flux. So Faraday's law is very much dominant in this case. Okay, as we all know, Faraday's law of electromagnetic induction. So the phi m, which is the mutual flux, is being transferred, and the coupling coefficient m is the important factor here, where we can, of course, the L1, L2 have to be designed for that. So the design aspect I will cover in this lecture also. For primary, there is, of course, there is leakage, because it is core, no core, coreless, or air core, you could say. Unfortunately, there is leakage flux. As you can see, primary and secondary is having leakage. How to minimize the leakage? Can anybody tell me? Anybody over here who is, you are all teaching this course, I believe also circuits also you teach, right? Some of the faculty may have been teaching resonant circuit in the AC circuits. Like, okay, so leakage flux, how do you minimize the leakage flux? Can you hear me?
Yes, sir.
So my question is, how do you minimize leakage flux? So anybody? Yeah, somebody is going to answer, I think. Shubham, do you want to answer the question?
Yes, sir. I think by adding the core into the coils, we can reduce the leakage flux.
Core means shielding. We are doing some shielding. Shielding is required in the. Of course, if you add core, the whole idea is not to have the core. Air, it is air. You cannot have that option of adding core to the coils. What you can add is, yes, ferrite core, which you talked about. Ferrite cores we can add as a shield. Okay, and you can distribute it around the coils. Is that what you are telling?
Yes, sir.
Correct. So that is very good answer. Fantastic, Shubham. What you will do is shield that one. The correct technical word is shielding the core, the coil with the ferrite cores. And I will demonstrate in the practical setup and the results. So in theory, you can shield it. Second, what you can do through circuits, what you can do? Through circuit work only. The
By
answer is
arranging the primary and secondary winding concentrically.
yes. That is another good answer, Deepak. Very good answer. And how about using compensation capacitors to resonate, to make it a resonant circuit? That will also give us some benefit of increasing M. Correct?
Yes.
Mutual flux. That is the most important, as I said. So you can see in the top circuit there, I have shown two capacitors in series with the inductors. Correct? So very clearly, there are quite a bit of solutions that we can use. Resonant circuit is one, shielding is another, as you said, and several others. So now on either side, of course, you need to create high frequency in kilohertz for the resonant circuit. So the power supply from DC link, I have not shown you complete circuit here. In fact, I think complete circuit is in the next diagram. Here you can see, starting from the supply, high frequency power converter is required with the compensation circuit. Then you have your loosely coupled coil pair. Finally, on secondary side, you want to charge the battery, so you have a rectifier, secondary compensation circuit and rectifier. Okay, that is your complete wireless charging setup. And of course, as I said, Faraday's law, Ampere's law are satisfied for this circuit. Okay. So here is one of the work that we are doing with this company SCAI. If you look up this company SCAI, it's a company in Canada which makes drones. We are working with an Australian company also through Government of Canada funding. This New Frontiers research proposal is basically encouraging working with international groups. So this Ripper Group is a company in Australia, and they use it for rescue, search and rescue missions. Typically, Australian group, this Ripper Group, is using this their drones for how you say beaches, oceans, looking for sharks. They have a spotter, shark spotter camera that can actually overcome humidity, etc., and they go over the ocean. So they are providing some drones, and SCAI is providing us some drones for the medical search and rescue missions. So we are also pursuing work of taking power from the power lines, transmission lines. That is one application. And other than that, we are designing the coils also for them for the wireless charging. So same story, primary coil powered by the AC, and then the drone comes and hovers around and has a pickup coil with rectifier, BMS and battery on board. So looking at some structures, this is some work done by Dr. Kunwar Aditya in the past, who basically works for Bob Warner now, one of my past students. He started looking at different configurations of the coupling. You are diving into a little bit of the detail of the coil design now. As you can see, we can either have circular pad, which is the common one. And as you mentioned, I think Shubham, you mentioned about the core, right?
Yes,
By
sir.
adding the core. So here is, I mean, you can see the gray spokes. This is the ferrite core, iron core. You see. So the coil, once is designed, the leakage will be reduced by adding the ferrite core. What it does, ferrite core, basically it will concentrate the flux in one direction rather than distribution. So when you do the finite element analysis of this structure, you will find these details before designing the physical coil. So a lot of finite element analysis has to be done, design and simulation. We also look at the D structure. So this is DD. Then there is D and Q structure. And finally, there is bipolar structure. So where you can see that the ferrite usage is less with this structure. So cost effective. So there is different configurations, and we are not restricted to only these. We have other designs also. And I'll show you one such design. So here is Kunwar's picture. I like to show the students' picture because see, this work is at the end of the day, it is not my work, okay? It is the student who did the work, not I am only the director and the I will give the blessing, but they are work. So the thesis, actually, if you download the thesis of Kunwar, you will find details. But okay, so the projects were being funded and now ongoing. We continued the work from Kunwar. Here you can see his experimental setup in the lab. Clearly, you can see this is a 3.7 kilowatt system. SAE J2954 standard. SAE J2954 tells you 4 levels of charging. Okay, 4 levels of charging is 3.7 kilowatt, 7.7 kilowatt, 11 kilowatt, and 22 kilowatt. Everything is zapping at 85 kilohertz, standard frequency of wireless power transfer, according to Society of Automotive Engineers. So what Kumar did is our first design in our lab. He was the initiator of this work. So this is, I'm talking 2016, 2015, he completed his PhD. He had started in 2012, 2013. So last 7-8 years we are working on this work, and he designed, in fact, in 2015 he finished, and he basically designed 3.7 kilowatt. E-Camion is one of the company, Transport Canada, Nova Bus, who is now owned by Volvo actually, and Forte Mobility now more recently are very interested in this technology for the buses, charging buses at bus stops. Okay, so I'm just showing you a very simple one slide summary of Kumar's work. There is so much details. I can talk about wireless charging for 6-7 hours. I have given one full day tutorial on wireless power transfer design from bottom up, from scratch. How to design the resonance circuit, how to overcome the bifurcation issues. Many details are there in the thesis actually of Kumar. Please pick up the thesis. It is freely available for download, by the way. You don't even have to email me. Just Google Kumar Aditya and thesis. Just Google it, will come. So anyway, his efficiency was close to 93% from the DC link input to the DC of the battery. Okay, 93% efficiency, which is quite high and well established. Here you can see the basics of the design of the spokes of the core, like ferrite core PC95. You can see here the core dimension, etc. I will not go into detail of that one. Vamshi, we work with, this is Vamshi. He finished, and in fact, when he finished, he was offered a job by Tesla. He joined Tesla for 2 years and left Tesla. Now he is at another startup in California itself. He worked with a company called Delta Q. In fact, we had a project for golf cart charging. Here is his setup. See, for golf cart, we went for bumper installation. The whole ferrite core itself, is basically the wireless power transfer unit, primary and secondary. You can imagine the transformer design we can do with how you say different shapes of cores, like how you design high frequency inductor, like a core or choke, like EI stamping, EE stamping, UU, CC, all those shapes. So we used FEA to design many. Again, his thesis has a full chapter on the design of this ferrite cores. So we decided on this UU structure. So U-shaped structure, and primary and secondary are 10 centimeter apart. As you can see, it is a 1 kilowatt charger and DC to DC efficiency of 94%. So bumper to bumper or bumper to wall, like one can be installed on the wall and other one is on the golf cart, and the golf cart can come and charge. So it reduces the load. I mean, carrying battery on the, like on the, this one on the golf cart can reduce, and also the plugged infrastructure. So the company was very happy with this kind of a solution. So 94% efficiency, quite comparable to the plugged version. Then same story, we installed the 3.7 kilowatt charger on bus stops. As I said, here we started working with Durham Region Transit, our regional transit authority. You can see a typical drive cycle here. This is a route of the bus. The bus number is 401, and the bus starts and goes through a loop, make a U-turn and come back to campus. So there is a campus here, and this is the downtown of Oshawa, our city where our university is, and it makes a loop and comes back, like bus depot is there. Okay, so the yellow stops we installed wireless charging, 3.7 kilowatt, all the yellow bus stops. You can see this is the drive cycle. We have measured the speed versus time on x-axis, and we have seen where all the stops are. Okay, as you can see, speed is going up. This is in kilometers per hour, and the speed comes down to stop. Then again starts and again bus stop. So we have measured a typical day of this bus, up and down. Okay, and it is a total 40-minute drive. Okay, 40 minutes for this whole drive cycle. So similarly, this cycle repeats throughout the day. So what we have done, we took an electric bus which we have in the city, and we started to install these things, and the result actually I will show you. The yellow ones are the wireless charging. Wireless charging occurs for like 2 minutes, 1 minute, while the students and people who are coming to campus are coming into the bus, getting off to the bus. You know, bus typically stops for 30-40 seconds, maybe up to a minute, and 3.7 kilowatt is good enough to top up the charge in the battery pack. So here is what we saw. If we didn't have blue plot, you see blue color, okay, battery SOC percentage is shown on the y-axis, state of charge. On the x-axis is the driving cycles. So that one cycle, you see this is called one cycle. Okay. Similarly, we are having 15 cycles. Let's say in a day, 15 trips are done. Okay. So what is happening? The blue one shows you the deterioration of the state of charge. By the time you are at the end of the day, it is at 10%. This big battery pack, usually these battery packs are in the vicinity of 200, 300 kilowatt hours battery pack. Then you need to charge it back again to 90%. Okay, that is a big stress on the charging infrastructure. Rather, you see the brown plot. The brown plot is with the wireless charging. This wireless charging yellow chargers that we put at the strategic stops. There, now we can see the mode of operation is charge sustaining. You do not let the battery deplete all the way to 10%. You can see between 70 and 80%, you can keep the charge profile of the state of charge. So what is happening? The battery is healthy, more healthy with the wireless charging because of the top-up charge you are providing at the bus stops. So during the day, you are left with the 80% SOC of the battery. You are not allowing it to go to 10%, which is fantastic. That means what yesterday's talk I talked about, those of you who attended yesterday will appreciate that the capacity left in the battery is huge. Now you can double the calendar life or even triple the calendar life, means in terms of years, how much the battery will last. Instead of doing this kind of profile, killing the battery whole day, you are now sustaining the charge in the battery. So that is fantastic application, in fact, for the buses. Then we focused our attention also on capacitive power transfer. So the circuit that I showed you earlier had the inductor, right, in the coupling. Here you are using capacitive coupling. So how basically aluminum, if you use aluminum plates, you can have capacitive coupling. Okay. 1 kilowatt capacitive transfer was designed by Deepak. This is Deepak. He finished his masters with me and joined a company in British Columbia. And now, in fact, he has come back and joined Volvo in Bangalore. He has come back to India and he has got a very high position, managerial research position in Bangalore Volvo headquarters for India. So, I mean, he's doing very well in industry. He worked for about 5 years in Canada and came back to India for his work with Volvo. So he just did this like last few months back. I just spoke to him and he's saying, Prof, I have come back to Bangalore. So I met him, in fact, when he was here. He is here rather, and he has started his job here. So anyway, he was working on this work. Now, in terms of the capacitive transfer, the compensation is inductive coils to make it resonant. Okay. Capacitive transfer gives you the advantage that all the disadvantages of inductive is offering. Like you can overcome some of the difficulties. What could be the difficulties of inductive power transfer, for example? Can you tell me inductive power transfer issues? What would be the biggest issue of inductive, high frequency inductive power transfer? How about electromagnetic compatibility, or EMI, electromagnetic interference? Correct? EMI, EMC issues. These are some things that is big issue. Inductor is also bulky, very heavy. Cost is very high. So couple of things that are very important. Capacitive power transfer is electrostatic power transfer. Inductive is electromagnetic. So electrostatic power transfer means now we don't have any issue related to EMI at all. Yes, there is high voltage discharge between the plates, right? Primary plate and secondary plate of the capacitor, positive and negative. It is an energy storage device. So you are creating a high discharge to transfer the energy. But at least the EMI issue is solved. Secondly, you know how this, how you say, foreign object detection. You know, foreign objects coming between the inductive power transfer unit can cause big problems, short circuits. It can cause reduction in the power transfer because the flux distribution is changed because of metallic object, foreign object. So detection of that is required. In capacitive power transfer, this issue is resolved. You don't have that issue. So capacitive power transfer, we started some work around 5 years back, in fact. And this is the 1 kilowatt system that we designed. Efficiency is high of 95%. One thing about capacitive power transfer is frequency goes from kilohertz, which we use in inductive power transfer, to megahertz. That is the disadvantage, because you want to discharge the air between the plates. The high discharge that we are trying to create in between the plates is caused by high frequency. You have to go up to megahertz. So the power electronic switches in the inverter, high frequency inverter, have to be selected for that. Like now MOSFETs are available, megahertz frequency, no problem. So up to 1 kilowatt or even up to 2.7 kilowatt we have demonstrated in the lab. This is Sang, a PhD student who graduated recently. He is from Vietnam actually, originally. We started to look at conversion stages. So how to reduce the primary side in one conversion stage. So, you know, in primary side, there is low frequency AC. You convert that to DC using rectifier. Then you convert to high frequency AC using inverter. Instead of doing double conversion and primary side, we have gone with AC to AC, direct AC to AC conversion using matrix converter. Some of you may have already worked on this or have the knowledge of matrix converters. So matrix converters are very popular in communication systems, aerospace systems. They have been used in the past. But for the first time, we demonstrated in the world for wireless power transfer. So Sang's PhD was on AC-AC converters for wireless power transfer systems to reduce the conversion stages. So it will be really less bulky and highly efficient. So all these matrix converters we pursued and designed in the lab. In fact, we tried all these on configurations. Single phase buck converter, single phase half bridge, single phase full bridge. Then we saw some high power 3-phase buck, 3-phase full bridge configuration, as you can see. So we have tried all kinds of AC to AC converters on the primary side. Okay. Here is a 1 kilowatt hardware setup. You can see here the coils, inductive coils. Here is the AC half bridge converter that was designed. DC power supply, you can see. Finally, the battery pack was emulated using our programmable electronic load. Here you can see the rectifier unit, half bridge rectifier unit on the secondary side, and inductive coils here, 1 kilowatt setup. Okay, the whole setup is shown here with the power converter. Okay, we also have a grid emulator. You can see at the bottom here in this picture. Here is a grid emulator. So it is bidirectional. Our converter can be bidirectional, whereby we can transfer power back. So as I showed in the previous schematic here, grid to vehicle and vehicle to grid is also possible, V to G. So it's a bidirectional inductive power transfer unit. Okay. Here you can see in the blue plot the THD, total harmonic distortion. This practical circuit gave us the efficiency of 94% almost. Here you can see the blue plot THD versus current, and a red plot is the efficiency versus current for 1 kilowatt system. So you can see at the maximum power output, you are getting almost 94%, 93.4 or higher. In some cases 94. So approximately 94. And you can see it is way better than the other bridgeless, boost derived, buck boost. So these are some references in the thesis of SCAI, which you can download as well. And you can see the number of switches that was used. 12 switches, 4 diodes, 8 switches, 6 diodes, 4 switches. And in our converter, 6 switches. So we have reduced the switches, number of switches. Our setup is 1 kilowatt. And you can see the input THD of the current. Percentage of the input THD is about 3%. This is without input filter, that also. If you put filter, in fact, we can go below even 1% of THD. And you can see efficiency 93.4. Okay. So that is your experimental setup for a 1 kilowatt with matrix converter. Highly proven technology now. And we have published a lot on this work. You can download papers also. Okay, so then going for the capacitive power transfer for drones. So Deepa actually, so this is one of the 4 drones we tested. Okay, DJI company, Freefly, DJI S1000, DJI F50, F550. All these drones have maximum payload. You can see 9 kilogram, 10 kilograms, 6.8 kilograms, etc. 0.5. Flight times are shown here. You see the flight time, how low. You see with 10 kilogram weight, 16 minutes, only 16 minutes. And battery capacity is about almost 500 watt hours of battery pack. And the weight is about 6 kilograms. So what we did is wireless power transfer from base station to the receiver drones, and then from receiver drone to the transmitter drone. You can do the capacitive power transfer in the air. So mid-air recharging as well as base station recharging is possible using capacitive transfer. So really you need these both technologies to work in tandem. You can have base station as inductive and mid-air recharging as capacitive. Okay, so these are very cool technologies that we can pursue. So we started to work on this. You can see there is a paper here on emerging technologies, the WOW conference, which is emerging technologies in wireless power transfer. And it was held in Montreal for the first time in 2018. And since then, we have always attended this conference. So Deepa and Sang and Dr. Lalit Patnaik, now all 3 have finished their PhDs. Of course, Dr. Lalit Patnaik was a postdoc. And Deepa and Sang just finished this year, last 2-3 months back, their PhDs. So here is Dr. Deepa Vincent. She basically designed this capacitive transfer unit. Okay, as you can see, we went for a hybrid system. So first she designed the capacitive plates. You can see the matrix structure of the aluminum plates, 4x1, 2x2 matrix. These are some finite element analysis of that. She also looked at the permittivity of different dielectrics, not just air. Of course, air is one at ambient temperature 20 degrees Celsius. You can see quite clearly air is one of the options, but other ones are there, like you can introduce paper, Teflon, glass, ceramic, then some inert materials such as lead zirconate, titanate, barium titanate, which are having greater than 5,000 permittivity. Okay, ceramic class 2 is even having sometimes greater than 2 lakh or 200,000, you know. So this is huge permittivities at ambient temperature. They depict so much high permittivity. Imagine the design. So we have done all these in finite element analysis. No doubt, I mean, cost will increase if you go for these class 2 ceramic, etc. So we have stuck to air. We have demonstrated hybrid, inductive and capacitive. Deepa basically demonstrated a 11 kilowatt system, class 3, standard 3 charging of using air as the dielectric medium. Okay, she introduced inductive plus capacitive. So we have also analyzed the voltage stress in the capacitive bank. Here is the capacitive power transfer unit and the voltage stress. So electric field analysis was done for a stress of 1000 volts between the plates. Okay, between the plates. So of course you know the formula from circuits, right? The voltage stress is nothing but inversely current divided by, directly proportional to the current divided by the reactance. So omega C, as you can see, okay, or multiplied by the reactance 1 over omega C. Okay. Finally, we used both inductive and capacitive, as I said, in the hybrid link and matrix converter from SANG. And that was in fact published. This work actually we demonstrated and published in IEEE Transportation Electrification Conference and Expo in 2017 in Chicago. Here you can see the coils and the capacitive plates, both. Okay, so both are there. You can see here the inductive coils. When capacitive power transfer is occurring, you can use the inductive coils as compensation for the capacitor. And in fact, the inductive coils can be designed also for the wireless power transfer. And strategically placing them in a coupling unit, you can get the power transfer. Then you have your compensators L1, C1 as usual. Okay. You can have capacitor in parallel or in series. In fact, there are several papers from Kumar Aditya showing the compensation circuitry and their characteristics. Okay, just from resonant circuits. If it is a series like the capacitor in series with the primary coil, or parallel with primary coil, or on secondary side series with secondary coil, and capacitor in parallel with secondary coil. What are the impacts and what are the characteristics and where you should use them? So those are some things based on your primary power supply and secondary charging profile. You have to decide as a designer. So a lot of analysis is there in the thesis, as well as papers have been published in last 8 to 10 years from our group. So look at those papers, how to place the compensation circuits. So here you can see the hybrid schematic circuit. This is the complete schematic, primary side, secondary side with capacitor and inductors. And this slide shows you the setup with Deepa, who created the, see the aluminum capacitive power transfer unit. Okay, and this is the complete setup, hybrid link with the inductive coils as well, inductive power transfer unit plus capacitive power transfer unit. Now, of course, we also went into the design of 7.7 kilowatts. So that was a hybrid schematic 11 kilowatt system. This is a 7.7 kilowatt hexagonal design, new design. Okay. So here is the parameters for that: 85 kilohertz, 400 volts, 7.7 kilowatt, 400 volts, 19.25 amps. So we went for an inductive coil design of 7.7 kilowatt. So here is the shape of the coil. You can see from circular coil, unipolar, to a hexagonal coil. What is happening here? We take the same circular coil and at the edges, we create a hexagon. So some material is cut. You can see quite clearly if we draw here, you can get a hexagon, okay, along the perimeter of the coil. So if I were to show you using a highlighter, if I were to draw sorry, this color is not. Let me. Okay. Let's try blue. Okay. Sorry. So if I show you on the edges what exactly is happening to the on the perimeter here. See, you see, if I cut this edge, correct, you can see that we will get a hexagon. So we are chopping some material out of the circular coil. This one and this one. So quite a bit of material we are cutting over here. So when you see, when we reduce the material of this leads wire, what we are doing is getting this one, hexagon. So when you get a hexagon shape, you are using less material and now it is cost effective. So very clearly, you can see here from 23 tons, we have reduced to 20 tons, and the weight is from 3.4 kilograms, almost 3.5 kilograms to 2.5 kilograms, which is now 1 kilo reduction in the weight. And 1 kilo out of 3.5 kilos is a big percentage. Okay, you are looking at about 30%, 25% reduction in the weight, total weight. For the same inductance, see what we have done is cleverly or smartly designed this coil so that the inductance value is not changing. No doubt, 128 microhenry, 126 microhenry. You can see the comparison. Okay. One thing we need to do is that now we have to restructure the cores. Even the core length, you see the core length or the material is reduced. We have cut the shapes of the core, we cut it and machined in our lab, and we use the cores and strategically placed for the shielding, okay, for the shielding effort, and we have placed it. So coming to the FEA analysis here, primary coil is as you can see circular itself, but secondary coil we have used our new design. Here is the magnetostatic simulation of the same, the flux density that is created by the primary winding, clearly shown here, circular coil. Finally, the eddy current analysis was done. You can see eddy currents are around the periphery. So you can see here, right? Eddy currents flowing through the coils in the skin effect. You can see the skin effects inside the coil and the distribution of the eddy currents. What we have done with the core structure, another thing very smartly done, was we concentrated the flux that was created by the eddy currents into the coils. Rather than wasting the flux, the eddy current, instead of taking the losses, we have used it smartly for creating flux transfer or assisting with the flux transfer. So that is very important work. First time, again, nobody had done this work, eddy current analysis and using eddy current for the flux transfer. So we have included that in the design itself. Okay, so it was adding to the flux density efficiency. Here is the FEA analysis showing the copper losses or variable losses, I square R loss in the coils. Okay, again, it is a flux distribution. You can see based on flux distribution how the losses are occurring. Then, of course, we did a core simulation with the power electronic circuit, seeing the power transfer from primary side to the secondary side. We used a Simplorer software and ANSYS. ANSYS Simplorer is used to create this transient simulation, and you can see the coil here. Okay. Here is the physical design of the coil. So you can see the error actually between the simulation and the practical design. See, you see the size of the coil. Just to show you the comparative size, we have placed a Sharpie marker pen just to show one of the edges of the coil along the length of one of the edges of the coil. Okay, here are the ferrite cores placed as I showed you in the FEA as well as the circuits, theoretical diagram. Here is the practical circuit, it's practical coil design. Okay, this is leads wires, high frequency. So 85 kilohertz is passing through this, and the current, of course, at the level. The value of the inductance is 126.5 microhenry, as I had shown you. Error is there, no doubt, 1% error, which is between simulation and experimental setup you can expect. It is very, very acceptable. Okay, it has a DC, of course, resistance, ohmic resistance of 40.36 or 40.37 if you round off, of milliohms. So it is DC, obviously. This is contributing to some I square R losses, copper loss, but not much variable loss. Here is the complete setup. As I said, it is a 7.7 kilowatt setup. Primary coil is circular, secondary coil is hexagonal. Okay. Some results I want to show you, of course, very quickly. It is now 11 o'clock, so we have another 1 hour. Primary voltage, secondary primary current, primary voltage, and secondary current, secondary voltage results, experimental results from that coil. Then, of course, shielding, right? So, okay, so core structure is fine, no doubt about it. But what about shielding? So we have gone for a new honeycomb structure. You see, this is the current distribution in the shield. We have designed the shield with honeycomb. Honeycomb means like beehive, the bees are creating this hive, and this is the structure. So all of these are hexagonal with air in between. So the coil, actually the aluminum foil made of aluminum, is made of the honeycomb structure, and we placed it on top of the coil. Here you can see the secondary coil. Here is the results. You can see some shielding with an aluminum plate, normal aluminum plate. This is our honeycomb structure, and finally the shielding of ferrite. See, ferrite is not giving much good shielding. Aluminum plate is much better, but it is compatible with our aluminum shielding with honeycomb. Now honeycomb is, of course, much more cheaper. If you use a whole aluminum plate, it is much more costlier. As you can see here, we are having less material usage. In the honeycomb structure, no doubt, almost 50% to 60% less usage of aluminum. So the cost again comes down, and you are having the same result, or maybe even better, you see, in terms of the shielding. Here is showing the thermal analysis. Even with the shielding of this structure, you can see it is a very cool structure. You don't have hotspots, much hotspots, except maybe 1 or 2 or 3 hotspots. But you can see overall, in the main part of the shielding, it is a cool structure. Okay. So this is your temperature, thermal analysis versus ferrite. You see, ferrite is actually showing you, okay, quite a bit of hotspots in the ferrites. That means what? You will have to replace these ferrites quite often. Whereas in our honeycomb structure, you will not have to replace as often. This will be longer lasting. So again, you are doubling or tripling the life of the shielding. So this is very important work. So inferences, of course, almost 30%, as I said, lower weight reduction. I told you in the beginning, right? For same power level versus circular, you can get 30% material reduction. Okay. We made a new honeycomb mesh for EMI mitigation. Okay. Efficiency is quite high, almost 97%. DC-DC. Okay. Now, moving on, we are exactly 1 hour. Second part of my topic is in plugged charging. Wireless charging, no doubt. I showed you all the applications, last 5 years work, actually recent work. Now, last 5 years, plugged charging work. DC fast charging, ultra fast charging, all those applications. So when you do charger, any charger, wireless or plugged, you must think of what you are trying to do. What is your load during charging? Philosophy of charging is what? So look at your cell phone, for example, or laptop. Now I'm presenting on laptop. I have plugged into the charger in the wall. Many of you also who are watching on laptop, tell me you are plugged in or not? You are charging? Correct? I am assuming you are not using battery pack. I mean, you are not simply using only the battery. You are charging. Same philosophy appears. We are always anxious. It is called range anxiety. Okay, range anxiety. My cell phone is also charging now. Like, if I am having opportunity to charge off cell phone, laptop, I will charge. Okay, if I am in a train, in a bus or something where there is no charger available. Even now they are giving the portable charger, portable charger with the battery bank, which we are carrying with us. Again, in bus or train or metro, wherever you are, you want to plug in to that portable charger so that your battery range is maintained. So you can see quite clearly the green plot. You see the green color? This is charging of any electric device. So here is the charging philosophy. Always we are worried about battery range. Battery is not a tank. When it comes to electric cars, the philosophy is, think of it as a mobile device. Laptop is not any different from cell phone, and it is not any different from electric car. It is a mobile device on wheels. Only difference is you are driving it. Okay, so it is a mobility device. That's why the term e-mobility, electric mobility, came into existence. I'm just saying fundamental, the psychology of humans. Okay, the philosophy of electric vehicles. So charging of electric vehicles should be thought of like this, where you do not let it discharge completely. Okay, rather you are topping up the charge from at regular intervals. So here the red one, now the red one is showing you the normal petrol car or diesel car, gasoline car. Many of us own the cars or scooter, whatever vehicle with petrol. We don't go to the petrol bunk or petrol station to fill the car when it is half tank, let's say half tank. If it is at half, do you go? You will wait till it is close to the empty. Correct? Correct or not? When it is close to empty only we will go. Oh, it is coming close to empty tank. Let's fill, maybe even then we don't go to full tank. We'll say a quarter tank or half tank. We will tell the person, or if it is self-service, you will fill. Like in North America, we fill our own. Mostly it is self-service. So basically the philosophy is different for petrol cars or gasoline cars. So that is the red plot. But in electric cars, it is not the same. As I said, it is like a mobile device. So we are always topping up the charge. So coming to our point, designing the charger. We don't need to design charger for the full tank or for the full battery. All we need is for maybe 25% of the battery pack or 50% to be safe. Charger design in terms of kilowatt hours or kilowatt. Okay. Here are the different charging levels. So Society of Automotive Engineers gave us the standard J1772, various charging standards in AC and DC. This is freely available for download. So you can see these standards online. I won't go into details. This is just pure data. However, I want to point out one thing. DC level 1, 2 and 3 now is becoming very popular for fast charging. When they say fast charging, anything from 36 kilowatt up to 240 kilowatt is available or designed. Now power electronics can do this, and I will show you some configurations for those. DC is also important because looking at the future grid, The microgrid will be more DC intensive with renewable energy penetration. And all renewable energy sources, as you know, have DC as the output stage, whether be it wind, solar, fuel cell, whatever you may use as part of the mix of the sources, battery packs, whatever. In the microgrid environment, you will be having DC. So coming to these DC levels of power is very important. Okay, and I will show you some work we have been doing. So here is some circuits from a paper for ultra fast charging. We published a paper in 2015, 5 years back. Now it has been the most highly cited paper in the literature for technologies or charger topologies for DC fast charging. The levels of charging. So here are the various levels of fast charging and different products of DC off-board fast chargers. So you can see Tesla, they have their off-board charger. Then EFA, which is more European standard, Tritium, Delta, all these companies, EVAC, they have an espresso charger. This is also I'm showing you the different parameters and the different companies with their fast chargers. And these are only a small, short list of companies. There are several other companies unlisted here, but I just wanted to show you the different types and different variations of fast chargers. So here you can see, 150 kilowatts, 50 kilowatts, 475 kilowatts from Tritium is the largest available fast charger. 150 kilowatts is more the common range, 120 kilowatt. So from Delta, EVTech, etc. So nothing but what happens in a fast charger is you tap into a distribution line, right? AC distribution level voltage. So that already you are working with high voltage in kilovolts. You are having the rectifier and PFC stage, input filter, rectifier PFC stage. Then you are having the isolated DC-DC stage. Finally, the output filter and the charging of the battery. Okay. So inside the isolated DC-DC stage, you are having the high frequency transformer. No doubt, DC to AC inverter, high frequency, and AC to DC rectifier on the secondary side. Like a typical power supply. Okay. In here is the innovation. In here you can use different configurations. Of course, from a microgrid standpoint, the grid looks like this, right? You can have a common AC bus configuration. So the medium voltage grid is here, as I said. MV line, you can have the MV to LV transformer, distribution transformer, low frequency. And then you have the AC line. So if it is an AC microgrid, then you can have the chargers for each car. It can be bidirectional DC-DC converter and inverter coupled as one, as a charger, and then having the power flow in bidirectional from the battery pack of the EV back to the grid or from the grid to the EV. You can have integration with renewables, which we do now. In fact, many of the configurations are like this, where you have the renewable solar or wind or fuel cell, which is unidirectional. So in one direction, they are pumping power into the AC grid, okay, through the DC-DC converter again and inverter. Okay, it can be a house, it can be office, whatever it may be, or solar farm. Like in Canada now, we are having solar farms, huge, vast acres of solar farms, which is fantastic, powering into the grid. Here you are seeing energy storage application, stationary energy storage or second life battery packs. We have recently embarked on a project on second life energy storage. Very great application where the stationary storage unit is powering from EVs only. Once it reaches 70-80% usage, we are using for secondary application. Okay, and pumping power to the grid. Or you can charge the battery pack again. So it's bidirectional. So these are all applications of common AC bus. Then you are having common DC bus, DC microgrid. What we are doing, we are removing the inverter from each stage, all these orange blocks. We are removing the inverter and putting it in front of the transformer. Here, you see, very simple solution. One central inverter and several DC-DC converters connected to DC grid. So this is a microgrid which is of the future, which is now actually we have demonstrated even at our campus, Ontario Tech. Yesterday I showed you. But for those who missed yesterday's lecture, today we can repeat the same. Towards the end, I will show you again some slides on microgrid, DC microgrid. Now, this low frequency transformer and inverter, we can combine into a high frequency unit and reduce the cost even further and improve the efficiency even better by using solid state transformer. So SST is now up and coming technology, not I would say within last 5-6 years. Those of you who know Professor Prasad NJT from Texas A&M University and several other professors who are Virginia Tech, Texas A&M, they are working on solid state transformer, including our university. We are working on SST, whereby, you know, we are including the rectifier from AC to DC, high frequency transformer and DC-DC in one full unit into the DC grid and pumping power into the DC microgrid, thereby reducing the size of this unit. The whole cost associated with low frequency transformer and inverter is eliminated. It's a fantastic solution and being used now, okay, for fast charging. So let's look at some of the topologies of converters. So here quite clearly you can see this is a unidirectional full bridge series resonant converter in one direction. It's a single phase. I'm showing you single phase configuration. Unidirectional, so you can only go from grid to vehicle. You can have bidirectional charger where you use full bridge, bidirectional converter at front end and secondary side rectifier as well. So you can have bidirectional charging. Here you can see you can reduce the cost quite drastically by using PFC boost interleaved converter. You can see the papers which we have published and you can refer to them. These converters, their details, analysis, all that has been provided in the paper. If you want to reduce front end rectifier stage, here you are using full bridge rectifier. If you want to go to the semi bridgeless or bridgeless, total bridgeless or dual PFC boost converter, then you can use slow diodes in the front end and use the boost converter interleaved configuration in combination with the slow diodes. So again, you are reducing cost even further. Finally, you can go fully bridgeless. Here is showing boost converter and bridgeless configuration. No front end rectifier at all. So the rectification plus boost conversion is done in one stage. It is a fantastic solution for reducing cost even further in your charger. Okay, so again, this is all single phase configuration. You can see phase and neutral, single phase. Another single phase configuration is using zero voltage switching full bridge converter. Full bridge converter interleaved with another full bridge. Okay, and then of course secondary side charging. Then of course power levels when you go higher. So when you have DC charging up to 36 kilowatts, this is fine. But when you go up to 120, 200, 250, then you start going at three-phase distribution level. In the distribution level line in kilovolts, then we start to use unidirectional boost converter, or you can go to VNR rectifier, or you can go to three-phase buck boost converter, which is bidirectional also. Okay. This is a new converter which we developed in our own lab. So you can see here, this is a three-phase, three-switch converter where the boost and the conversion stage, charger stage are integrated into the same converter. It is a modification of Vienna rectifier itself. Okay. So you can see quite clearly here. The paper we have published is in APEC conference, Applied Power Electronics Conference and Expo, which was presented in Tampa, Florida in 2017. Janmajaya Channegowda, who completed his PhD in our group, and Dr. Najat Abdul Aziz, who was a postdoc at that time, both of whom actually created this work. So you can see very clearly our 10 kilowatt infrastructure. So here is the product, TPTS converter, which was developed in the lab, a 10 kilowatt system. Here you can see the regenerative grid simulator. Here is the DC electronic load, which is, sorry, Sanket, can you please mute your mic? Sanket? Sanket Walse, thank you. Um, we use the TI microcontroller for the control purposes. This is Janmajaya. Then we have one other cool product which we started working again, I would say almost last 8 years. 5 students till now have completed PhD on working on PV grid EV integration. Okay, so power electronics. So what we did was using EV as a bidirectional source, charging as well as discharging into the grid. And solar can also charge the EV and power pack into the grid. So many power flows can be done because of electric vehicles. Before, let's say a decade back, when electric vehicles were not there, solar was only powering power into the grid. Okay, there was no power flow here. So the inverter was having only single application, converting the solar back to AC and into the grid. Now with electrification of transportation, this is possible. Okay, charging and discharging the battery pack of the EV into the grid, and solar powering the grid and solar charging the vehicle. Okay, so one of my first students who started working on this was Gianpaolo Carli, Italian student but Canadian citizen. He started working on this, and then of course several other students continued. The future of course is quite clear. We can make charging stations. Okay, and in fact working here in Bangalore with some of the companies like Mahindra Electric, and in fact in the past it was called Mahindra Reva, and in fact Reva alone. Okay, Reva company which sold to Mahindra, then they became Mahindra Reva, and when Mahindra completely took over, they became Mahindra Electric. They are looking at solar as a solution. So Chetan Maini, who was the CEO and owner of Reva at the beginning, came up with this idea of solar tree or solar farms for charging. Now many gas stations or charging stations now of the future will look like this, with solar panels on the top. Okay, so again looking at DC microgrid of 2 configurations. Either way, you need the DC-DC chargers for the cars and the DC to AC inverter rectifier connecting to the grid. Okay, and interface with the solar panels. So you can see the solar modules, individual modules or bank of modules. We have started work with eCami and Solera to develop these chargers for them. So one thing is quite clear. Either way, you need 2 conversion stages. 2 conversion stages, DC-DC or DC-AC or AC-DC. So this 2-stage conversion can be reduced to 1 stage. We have been able to convert the conversion unit, reduce the conversion unit to 1 stage. And by using a Z converter, Professor Fang Peng was the inventor of this converter for renewable energy interface. So PV connected to single phase grid, for example. But we used the PV, the grid, and we integrated electric vehicle in the energy storage stage of the Z converter. So here you can see how we transform this converter into a single stage power converter, such that the vehicle, the grid, and the PV are all integrated into one black box. Okay, a great product actually for a business case. Here are the design specifications. It is a 5 kilowatt system. So we compared our technology with other work such as high frequency transformer based topology. There is a transformer-less topology. Again, 5 kilowatt system was designed in our lab. We designed our own Z converter, 5 kilowatt, modified Z converter, as I said. Siddhartha continued the work from Giampaolo, and we showed level 2 charging, DC charging. Okay. Here are the efficiencies of the power flows versus power output. So up to 5 kilowatts, we have transferred power, and we have compared Z converter with the other two topologies which were popular, high frequency isolated topology and the transformer-less topology. So clearly you can see it is competitive for all the power flows that I showed you. PV to battery, EV, PV to EV, grid to EV, PV to grid, and finally EV to grid. Okay, light blue color plot. So all four power flows are shown here. For Z converter, high frequency isolated topology and transformer-less topology. While you see all the plots are distributed, no, even like 3 plots are inefficient. The yellow plot is most efficient, which is PV to grid for this isolated topology. Transformer-less topology, 2 plots are efficient, 2 are inefficient. Whereas in our Z converter, 1 is inefficient but still competitive, which is basically the classic PV to grid. But for 3 power flows with the EV involved, you can see it is almost 96% efficient. Okay, so our converter on an average beats out the other 2 in terms of all power flows, all 4 power flows. These 4 power flows which are most important, which are possible, all possible power flows. So therefore, Z converter shows a lot of promise. So we started using this work for demonstration with the company Solera and eCamion. Praneeth Jayasai now works with Delphi Automotive. He finished his PhD also this year, 2020 itself. We have a patent granted, US patent. This patent has been granted. You can freely see it online. If you type this number or put JSI Sheldon Williamson patent, you will find the patent. We basically built a universal charger, on-board charger, okay, which is a buck boost technology for variable voltages for across the world. You can use this converter. Our converter can be used anywhere in the world. So 2 companies, in fact, want to buy the patent now. They make chargers. They have been in touch with us, Ficosa and Brusa, 2 leading companies in the world who are interested in this work. Here are the experimental results from the experiments. All these results we have put it in the patent application, I mean in the patent document. So here you can quite clearly see the voltage levels, right? 200 volts, 150 volts, 450 volts. Any charging input voltage you can use to get these output DC voltages. Okay. Efficiency with resonant conversion. So I think there is noise. Preeti, thank you, Preeti. Please mute your microphones. Blue plot shows you with zero current switching. So we have made our circuit resonant with zero current switching. Here you can see the blue plot, 95% efficient, up to 1 kilowatt charger, and at maximum power without, you are getting 94%. So again, you can see quite clearly almost 1% differential in efficiency between zero current switching and non-zero current switching, non-resonant circuit. Then of course, Automotive Center of Excellence. Those of you who missed yesterday, this is some drone work going on inside our lab, inside the Center of Excellence. So we have tested the drones. Here you see for the wireless charging of the drones, the drone is flying in the wind tunnel. Okay. And you can check for the misalignment, charging efficiency, and wind gust. You can go up to 250 km/h wind we can create cyclone inside this automotive center of excellence. Here you can see you can create minus 40 degrees Celsius to up to plus 60 degrees Celsius. You can create rain. You can create ice rain with cold temperature, minus 40 plus rain, how the rain freezes and how the electric bus can perform under those conditions. There's a good team of technicians, as I said. The technicians are so helpful to our students. In fact, students get tremendous help in building products. Like we cannot otherwise, and safety, you cannot just let the students go and build electric vehicle. I mean, you need to have technicians who are, how you say, trained for that. Okay, so they are 24/7 available, and we have access to the labs. Prime Minister, of course, gave us a $35 million funding from federal government. This is also as of earlier this year, very recent announcement. And this link will show you the video of the ACE tour, if you want to take a tour of this automotive center of excellence. So let me see if I can click this. Okay, how, if I come out, pointer option, laser pointer, arrow option. Let me know if you can see the video, okay? I hope you can see it. Let us see. Can you see the video? Okay. Is audio coming? Oh, just a minute. No audio. Why there is no audio? I don't understand. Now? Okay. So you saw that experience, virtual reality experience of automotive center of excellence. So it is truly one of a kind. Okay, in the world, nobody has such a facility where you can test for all those weather or climatic conditions. So I mean, even Prime Minister, Right Honorable Prime Minister of Canada, Mr. Justin Trudeau, he was blown away. No pun intended, of course. 280 kilometers per hour wind. We can experience cyclone effect inside the wind tunnel, and ice and rain and snow, etc. So you can test your vehicles. Now it is not only used for vehicles. We can use we can test even, how you say, buildings. Like you can bring construction site, like houses, buildings, anything portable. Like you can build, aeroplanes. We have tested even jets, drones, as I said, aeroplane sections, Boeing company, and like we have done projects with so many companies, and they come and test their facilities. So finally, of course, we are building a wireless power transfer unit inside this system, ACE.
तिथे
So,
रामराव आदितला होते ना,
sorry, Deepa.
रामराव आदित कॉलेज नाही का ते?
Huh. Deepa, I can hear you. Hello. Deepa, can you mute, please? Mute. Hello. Hello. Okay. They are not muting. Deepa, please mute your microphone. I can hear disturbance from your side.
Sir,
Thank
now
you.
it is muted, sir.
Barabar. And Brushali, yeah, thank you. Thank you for muting Deepa, madam. Acha. Now, last couple of slides, people who missed yesterday's talk, I just wanted for their benefit. What we are doing with the UIT or Ontario Tech, ACE Center is adding the EMI compatibility to the walls up to 250 kilowatts wireless power transfer test infrastructure. We are building inside this center ACE. Inside this ACE, in these walls, you see the walls. Now you are not having wireless transfer. On this dynamometer, when we have the vehicle, this is one wind tunnel, but we are having 4 wind tunnels like this in this facility. 4. So we are taking one, which is the main wind tunnel, which you saw in the video, and converting it into a wireless charging infrastructure with the walls, except the floor. Of course, the walls are EMI compatible. So here you can see we are adding this capability. So we are calling it the YTech Lab. And this YTech Lab will also be first of its kind in the world. Along with the environmental conditions, etc., we can add wireless power transfer EMI compatibility. Then it will be interoperable with the e-transportation test facility which we are having. We are already having microgrid, we are having e-transportation test facility, we are having the automotive center of excellence. There is a lot of research in AI and IoT, as you saw. But if we add now to this static and dynamic wireless charging, interoperability, as I said, between the two structures, the EMC compatibility, and finally performance testing and safety testing capability, then we are having an impact on global stage. And this whole lab will be accessible remotely through cloud. You can have a company in India, let's say Mahindra. So we have started talking to Tech Mahindra. Tech Mahindra, with their autonomous cars, want to work on wireless charging. They are very interested in wireless charging. So when I had talks with their CTO, Mr. Ramachandran, Dr. Ramachandran, he basically told me that he will be most interested, and we have signed an MOU with them and an NDA of non-disclosure. So the work has already started, where they can test their autonomous cars charging wirelessly here in this test facility, okay, which is fantastic. In fact, for something where we can make impact on a global stage, especially now during Corona impact, because last couple years, I think last year now 2020 plus 2021, nobody knows how much of the impact Corona will have on testing, like lab testing. The minimal amount of people involved in testing hardware, the better, because of the spreading of the virus. So therefore, we are looking at remote testing labs. So this lab will give you that facility. So the provisions are already made for that. So it's ongoing work. We are still building our lab. By 2021, hopefully by the end, we should have a fully functional wireless charging test facility. In fact, the company TDK is building its magnetics, the magnetics company TDK. You may be aware of this company. Okay, Government of Canada is obviously funding the project, and TDK is the company who is leading the effort. And CSI Shielding is a company in US who are contractors. They are doing the shielding work. Microgrid, as I said yesterday, I just presented very quickly. Microgrid is a combination of companies collaborating with our university through Panasonic, GE, utility companies such as Oshawa PUC and Hydro One. Here is the distribution unit, and you can see the solar panels with the distribution substation in our campus. Panasonic have given battery pack up to 500 kilowatt hours. So you can see the rating. Sorry, Sonali, can you please mute your microphone? So Panasonic's battery packs are on our campus, lithium-ion battery packs. And it is 2 modules of 250 kilowatt each, giving us 500 kilowatt hours. Sonali, can you please mute your microphones? Here is the Clean Energy Research Lab, exterior view. You can see the exterior view. And on top of that is the panels. This panel, solar panel, is actually sitting on this building. Our lab, there is one lab called Clean Energy Research Lab. Okay, so on top of that is the solar panels. And we are also on the SCADA system, as I said, monitored by Oshawa PUC and Hydro One, the utility companies. Here is our microgrid at the bottom. Solar panels are shown plus the energy storage units, battery energy storage units. So with that, I will end my talk. This is our lab's capabilities. As I showed you today, we talked about chargers. Yesterday, we talked about energy storage units. We have not covered drives in this lectures because I'm sure in the rest of the FDP, you are going to listen and hear about electric drives a lot. We have a lot of projects ourselves in electric drives as well. But in last decade, we have done so much work in drives. We have work with grid interface also, as I showed you a little bit today. We have worked on electric machine design as well. Okay, and the motor drive. We have also done electric machine emulator work. You can see some of the papers and thesis of students. So really, when we cover transportation electrification, you are looking at the complete cycle from grid all the way till the motor, which drives the wheels, and different configurations of chargers, battery storage units using supercapacitors, BMS. So battery pack, obviously, but supercaps, cell level BMS, I showed you yesterday, and protection units, and drives and machines. So we cover the whole spectrum, and it is in a cyclic manner. So students get trained across the whole spectrum. With that, I will end my talk. Thank you very much for listening. We can take some questions for next 10-15 minutes if you have any questions. Thank you.